Section 12 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 9, The Sun, Part 2. Before sunspots were clearly observed with the telescope, it was assumed that they were due to the transit of Mercury. Even Father Scheiner, after his telescopic studies, suggested that the spots might be small planets revolving around the sun and appearing as dark objects whenever they passed between the sun and the observer. It was recognized, however, that the spots appeared to move across the face of the sun from the eastern to the western side, or roughly from left to right. Father Scheiner's view was also held by Jean Tarde, canon of Sarlat, by Father Maupertuis, a Belgian Jesuit, and later by William Gascoigne, the inventor of the micrometer. Galileo, however, advanced a cloud theory, while Simon Marius, astronomer and physician to the brother Margraves of Brandenburg, proposed the ingenious slag theory, according to which the dark spots were the cindery refuse of a great solar conflagration, and occasionally expelled in the form of comets, which afterward blazed up with renewed vigor. Galileo, in a controversy with Father Scheiner, proved him wrong in his planetary theory, while the occurrence of the comets in 1618 won supporters for the theory of Marius. Galileo also ascertained the rotation of the sun in a period of between 25 and 26 days, as well as the general zone of the sunspots. The next important contribution to sunspot theory came from Derham, whose observations were made during the years 1703 to 1711. He believed that the spots on the sun were caused by the action of some new volcano, whose smoke and other opacious matter produced the spots. As they decayed, they became half shadows encircling the darker portions, and finally became bright spots. Lalande, the celebrated French astronomer, believed that the spots were rocky elevations, about which the penumbra represented shoals or sand banks, while around flowed enormous oceans. Lalande's explanation, as well as that of Derham, was clearly based upon terrestrial analogies, which were employed with considerable frequency by early astronomers. In 1769, Alexander Wilson of Glasgow (1714 to 1786), examining the large sunspot visible that year, noted that as the sun's rotation carries a spot across its disk, there was a change in its appearance, and that the same effect of perspective was produced as if it were a saucer-shaped depression, the bottom forming the umbra or central black spot, and the sloping sides the penumbra or surrounding portion of half shadow. The penumbra appeared narrowest on the side nearest the center of the sun, and widest on the part nearest the edge. Hence Wilson assumed that the great and stupendous body of the sun is made up of two kinds of matter, very different in their qualities, that by far their greater part is solid and dark, and that this immense and dark globe is encompassed by a thin covering of that resplendent substance from which the sun would seem to derive the whole of his vivifying heat and energy. Wilson went on to explain that the excavation of spots might be occasioned by the working of some sort of elastic vapor which is generated within the dark globe, and that the luminous material, which was more or less fluid, was acted upon by and tended to throw down and cover the nucleus. Sir William Herschel devoted considerable attention to the sun, and observing the variation in the sunspots, reached the conclusion in 1801 that it indicated a certain variability in the total amount of solar radiation, which he assumed might have some connection with terrestrial phenomena, especially the weather. He endeavored first in 1801 to trace connection between the price of wheat, naturally influenced by the effect of weather on the crops, and the occurrence of sunspots, claiming that when the latter were scarce there was a diminished solar activity, which caused colder weather, with obvious results. Ingenious as this theory was, there were not sufficient substantiating meteorological data. It finds, however, a counterpart in modern studies of the sun's heat, not necessarily connected exclusively with sunspots, however, whereby it is hoped to establish some useful knowledge of the relation between the amount of heat radiated from the sun and weather conditions on our earth. Herschel's observations of the sun and sunspots were continued by his son, Sir John Herschel, at the Cape of Good Hope, 1836 to 1837. John Herschel assumed that their motion was due to fluid circulations similar to those producing the trade and anti-trade winds on the Earth. The spots, in this view of the subject, he said, would come to be assimilated to those regions on Earth's surface where for the moment hurricanes and tornadoes prevail, the upper stratum being temporarily carried downward, displacing by its impetus the two strata of luminous matter beneath, the upper of course to a greater extent than the lower, and thus wholly or partially denuding the opaque surface of the Sun below. Such observation of sun spots, made with considerable thoroughness by the astronomers mentioned, as well as numerous others, did not establish any regularity in their appearance or effacement. It remained for Heinrich Schwab (1790 1875) at Dessau to announce in 1843 that the sun spot phenomenon reached a maximum probability in a decennial period. This announcement, although coming as it did after a patient study of the Sun, attracted no particular attention until a series of sunspot statistics were published in Humboldt's Cosmos. Then the correctness of Schwab's observations and deductions was apparent to all. When compared by Dr. John Lamont and Sir Edward Sabine with various periodical magnetic disturbances, it was found that the two cycles of changes agreed with extraordinary exactness. It was a remarkable coincidence that the observations of a number of investigators were in complete harmony. A study of sunspot records established the decennial period more correctly at 11.11 years. Thus commenced a recognition that magnetic disturbances on the Earth were related in some way to sunspot phenomena. For many years no direct connection could be established, although various theories were forthcoming. Likewise, further attempts were made to identify the variations of sunspots with meteorological phenomena, but without success, until Wolf in 1859, by an examination of the Zurich chronicles (1000 to 1800 A.D.), found data which established occurrences of the aurora borealis to be correlated with a disturbed condition of the Sun. From this time on, the influence of the Sun on terrestrial conditions assumed new importance. The beautiful phenomenon of the aurora, which consists of a glow in the sky about the north and south poles, had been observed for ages, but the first scientific connection of importance recorded was in 1716, when Halley stated that the northern lights were due to magnetic effluvia. In 1741 Hiorter at Upsala observed that they produced an agitation of the magnetic needle. This connection was further demonstrated by Arago (1819), so that by the middle of the 19th century the connection of the aurora with the Sun, and in turn with terrestrial magnetism, was as evident as it was insufficiently explained. The first result of modern study of the sun spots was to put an end to the old notion that there was a dark and cold interior of the Sun, and that the sun spots were merely rents in the brilliant cloud covering through which the interior portion could be seen. The late Professor S. P. Langley, one of the most active of the modern students of the Sun and its surface, thought that the filaments, which taken together constitute the penumbra, were everywhere present on the surface. Professor Hale states, he regarded them as resembling the stalks of a wheat field seen on end in the undisturbed photosphere, and revealing more of their true characteristics in the penumbra, where they are bent over and drawn out toward the central part of the spot. Langley believed that we are observing clouds of luminous vapors rising from the Sun's interior, the seats of convection currents which bring to the surface the immense supplies of heat radiated by the Sun into space. Separating these luminous columns are darker regions, characterized by a lower degree of radiation. The minute details can be recorded only with the greatest difficulty. Under ordinary atmospheric conditions the solar image is not seen as a sharp and well-defined object, but its details are continually blurred by the effect of irregularly heated currents in our atmosphere. Even under the best conditions the moments of very sharp definition are few, and the greatest patience and perseverance are required on the part of an observer who would record his impressions of the solar structure. At the best, drawings based upon visual observations must be unsatisfactory, since even the skilled hands of Langley could not secure the perfect precision which is so desirable. It accordingly might be hoped that here, as in other departments of solar research, photography would afford the necessary means of securing results unattainable by the eye. Unfortunately, however, this hope has only been partially realized. The influence of sunspots is not confined to magnetic and electrical phenomena. The researches of Koppen, which have been confirmed by Newcomb, show that the average temperature of the Earth, determined by the combination of a great number of thermometric observations made at several stations, indicated a fluctuation of 0.3 degrees to 0.7 degrees Celsius during the 11-year sunspot period. In other words, the temperature of the Earth's atmosphere indicates small fluctuations which correspond with the sunspot period, thus indicating that the solar heat radiation varies with the number of the sunspots. The mean temperature of the Earth is greatest at the time of minimum sunspots and lowest at the time of maximum sunspots. Hence the determination of the amount of heat radiated by the Sun at various times, especially at sunspot maxima and minima, is a matter of considerable terrestrial importance. The study of the sunspots, carried on by Professor Hale with the spectroheliograph and other apparatus, including special red sensitive plates of considerable speed, reached an interesting stage in 1908 when it was demonstrated that sunspots are centers of attraction which draw toward them the hydrogen of the solar atmosphere. Subsequently it was found that these spots are the seats of great cyclones, in which cool hydrogen gas is set whirling and is sucked down in the great maelstrom of the Sun, rushing into the center of the spot at a rate of about 60 miles a second. Consequently, the spots are the center of great solar disturbances which are of an electromagnetic nature. According to the modern electronic theory of matter and electricity, electrons, or minute particles of matter, in their terrific cyclonic velocity, produce magnetic lines of force. It was found by Professor Zeeman that when light is passed through a strong magnetic field, the lines of the spectrum are subdivided and appear double. This Zeeman effect Professor Hale has found in the spectrum of the sunspots. If one looks at the center of a spot, the light travels in the direction of the axis of the whirl or cyclone, while in viewing a spot at the edge of the Sun, the direction is at right angles to the axis and is manifested accordingly in the spectrum. This theory has been thoroughly confirmed, so that today it is known that sunspots are magnetic fields of great intensity. The important discoveries made by Professor Hale and his associates may thus be summarized as follows: First, that the spots are cooler than the surrounding region. Second, that they are centers of violent cyclones. And third, that they are magnetic fields of great intensity. In addition to the sunspots, the photosphere includes other interesting features, notable among which are the faculae, little torches, so named by Father Scheiner. These bright globular objects, besides the sunspots, are the only other phenomena of the Sun's surface visible by direct observation. Schroter showed that the faculae are heaped up ridges of the disturbed photospheric matter. Secchi and Young assumed that the faculae are the result of violent eruptive action of the sunspots, but it remained for the spectroheliograph to give a clear idea of their nature. Professor Hale states that they are usually most numerous in the vicinity of sunspots, and near the Sun's limb they are sometimes very conspicuous brilliant objects covering large areas. Near the center of the Sun, however, they are practically invisible, though faint traces of them can sometimes be made out on photographs taken with suitable exposure. This increase of brightness toward the Sun's limb is assumed to be due to the elevation of the faculae above the photospheric level and their escape from a considerable part of that absorption which so materially reduces the brightness of the photosphere. Rising above the denser part of the absorbing veil and thus suffering but little diminution of light, they appear near the Sun's limb as bright objects on a less luminous background. The chief difference of the faculae from the rest of the photosphere lies in their greater altitude, as photographs have shown that they may be resolved into granular elements similar to those constituting the photosphere. But they are the regions from which immense masses of vapors rise to the solar surface, and for that reason are important in the solar mechanism. Near the edge of the Sun their summits lie above the lower and denser part of that absorbing atmosphere which so greatly reduces the Sun's light near the limb, and in this region the faculae may be seen visually. At times they may be traced to considerable distances from the limb, but as a rule they are inconspicuous or wholly invisible toward the central part of the solar disk. The Kenwood experiments had shown that the calcium vapor coincides closely in form and position with the faculae, and hence the calcium clouds were long spoken of under this name. In the new work at the Yerkes Observatory, the differences between the calcium clouds and the underlying faculae became so marked that a distinctive name for the vaporous clouds appeared necessary. They were therefore designated flocculi, a name chosen without reference to their particular nature, but suggested by the flocculent appearance of the photographs. With the spectroheliograph, Professor Hale relates, it was at once found possible to record the forms, not only of the brilliant clouds of calcium vapor associated with the faculae and occurring in the vicinity of the sun spots, but also of a reticulated structure extending over the entire surface of the Sun. From a systematic study of spectroheliograph negatives, in the course of which the heliographic latitude and longitude of the calcium clouds, or flocculi, in many parts of the Sun's disk were measured from day to day by Fox, a new determination of the rate of the solar rotation in various latitudes has been made. This shows that the calcium flocculi, like the sunspots, complete a rotation in much shorter time at the solar equator than at points nearer the poles. In other words, the Sun does not rotate as a solid body would do, but rather like a ball of vapor, subject to laws which are not yet understood. End of section 12.